So online banking vulnerabilities are a serious problem. Many countries have large amounts of fraud, but the UK is one of the few countries which discloses publicly the overall levels. So that's what I will use for the example here. Now, there are a growing number of online banking users. So between 2001 and 2007, there was a 174% increase. So over that 6-year period. But over the 1-year period of 2007 to 2008, there was a 185% increase in the amount of fraud. So clearly the fraudsters like online banking too. The UK is fairly primitive when it comes to banking security, so the majority of frauds that we see in the UK are fairly unsophisticated. There's an example of it over here. It's just a standard email that says in fairly bad English that you should click here. When you go there, you'll be sent to a banking website that looks very like Halifax but has some bad English too, and it will ask you for your password. And the Halifax still will use just a static password in order to log in. There are slightly more sophisticated techniques, such as using keyboard loggers to get your password that way and then send it off to Russia for fraudulent use. And although these are very simple, they've been around for decades, they're still in use in the UK. In order to defend against this, some banks have released some security measures. A very simple one to defend against keyloggers is where you no longer enter in your password as normal, but you type it in, or you have a combo box to select which passwords, a few characters in the password. This is trivially bypassable because you just get a keyboard logger which also captures the screen at the same time. Another one is to try to defeat phishing websites. Here, the website shows you an image that you uploaded and is personal to you, along with some memorable phrase. And if you go to a bank website, or what you think is a bank website, and it doesn't show this, then you know this is suspicious. This is, again, trivially bypassable. All you have to do is do a man-in-the-middle attack where the fraudster goes to your bank, logs in as you, gets your image, sends it back, and then puts it on the phishing website. We can get a bit more sophisticated and use device fingerprinting. So this is a very wide collection of techniques where the bank website looks at some information about your browser, maybe it looks at the cookies or which version you're using and where you're coming from, and sees whether this looks suspicious. And if you see, for example, most of the time you log in from the UK using Internet Explorer, and then today you're logging in from Moscow using Firefox with a Russian language setting, that's probably suspicious, and maybe you shouldn't let them log in, or maybe you should look at their transactions a bit more carefully. Again, this is going to be quite easily bypassed. And another one which will be familiar to users in Germany are TANs and ITANs. I've got a bigger example here for non-German users. When you do some sort of bank transfer, this is with the ITAN system, the almost most recent version. At the bottom, it will ask you for ITAN number 35. You've been sent in the post a piece of paper which has a list of random numbers. You look up number 35, you type it in the box, and if that's correct, your transaction goes through. So this is all fine and well, except when you do a man-in-the-middle attack. Then you log into the online bank, get the ITAN index that the bank wants, you ask the user for that, and then you carry out the fraudulent transaction as normal. The way that criminals are breaking all these techniques is something called the man-in-the-browser attack. This is where there's code embedded inside your browser which manipulates what you're seeing and manipulates the data as it's going back and forth with the bank. So this defeats all of those measures because you are looking at your bank website most of the time, except when the fraudster doesn't want you to. So any picture passwords are still there. You are using your own web browser, so device fingerprinting doesn't catch it, and it's coming out of your network connection, so you can't use IP-based geolocation to try to spot that sort of attack. And Similarly, with one-time passwords, these are just really back and forth. And what this sort of looks like when the criminal does it is you are looking at your computer and then you want to pay to one account, but actually the screen that is being sent to the bank is paying to a completely different account. But you type in your TAN here and that gets copied over there and goes all the way off to the bank. The more sophisticated bits of malware will not only do this, but they will patch up your online statement on the way back, so it looks like you paid who you're going to pay, but actually you paid someone completely different. So the way to try to defeat these sorts of attacks is to do find some way to bind the transaction, so who you're paying to and the amount, to the authentication process. The problem with ITAN is, although these are one-time passwords and they're cryptographically secure and everything is good like that, TAN for one transaction is good for any other transaction. So some of the German banks have rolled out another system which is still based on ITAN, except the acknowledgement screen is not text, it's an image rendered by the bank. It's got some funny lines on it to make it hard to OCR, and it's got your date of birth in the back. So this means that the fraudster needs to take this image, do OCR on it to try to extract the TAN index, then generate a new image which has got your date of birth on it, and has the account number that you think you're transferring to. So this requires a little bit of OCR knowledge, and this is not hard, but it's not trivial, and what the criminals did was trying to move to other banks who are easier targets. So this did improve the situation, but it wasn't perfect, and now more banks are moving to systems like this. The fraudsters are trying to get a little bit of knowledge about OCR, and what I've heard is that they're being fairly successful at that. So all the banks are now looking at new ways to authenticate online transactions. What the UK have done is use your standard smart card that you use for ATM transactions and point of sale, and given you a little thing that looks like a calculator. Here's one of them, here's another one. So this is the one that's rolled out by Barclays, and that's produced by Gemalto, Gemalto. This one is produced by Xiring, I think, and that's used by NatWest and RBS. And there's a few other banks that have used similar techniques. These are based on the EMV standard, but they're specific to the UK, but compatible amongst all the UK banks. So you can use any one of these with any UK card. Other countries have rolled out slightly different systems that aren't compatible, but they're based on the same fundamental technology. They're fairly well designed, they're quite cheap. They simply have a little processor, a smart card reader, some big batteries, because these are supposed to last for years, and a keypad. The ones in the UK just do this, the ones in other countries are also calculators too, which are sometimes useful. What the user sees is that they put in their card into this reader, and they can use any reader. It's not personal to you. They're shipped out in big boxes by the banks. The card reader asks for your PIN. If you type in the correct PIN, it continues. You then are asked to enter in some details about the transaction, and then the card reader will display an authorization code. It sort of varies between 6 and 8 digits, depending on the bank. And the bank checks if that transaction, that authorization code is correct, and if it is, it allows the transaction to go through. Now, the protocol here is secret. There is a little bit of information known about how it's supposed to be used, but nothing about the cryptography or how it even interfaces with the card. And secret security protocols are sometimes problematic, so what me and my colleagues are trying to do is reverse engineer this protocol. So this is essentially a simple computer and a smart card reader, and we wanted to look at the communication between the smart card and the CPU. Another thing we could do is try to extract the code from the CPU, but that was going to be hard because these things are potted, there's no external flash chips we can read, so we decided to do black box reverse engineering and then just look at the inputs and the outputs. So this is what a smart card chip looks like, or that's the contact. The chip is actually a tiny thing over here now. There's some standard communication, or standard lines is VCC gives the card power, it's 5 volts, and there's ground, there's reset for kicking the card to sleep and awake, but the interesting ones are clock and the input-output line. There's only one input-output line. This is what the card looks like in the full scale. So here are the various connections, the mag stripe, and this is where your card numbers are going to be printed. The smart card protocol is called ISO 7816, and it is half duplex because there's one communication line, so either the card is talking or the terminal is talking. It can never be both. It's serial because, again, there's one communication line. You send one bit after another rather than sending a whole byte at a time. It's asynchronous. So this means that the clock does not synchronize when the card sends. All the clock does is causes the CPU on the card to keep running, and the frequency is important but not the phase. So this is different from the synchronous communication protocols where the clock changes and then the data appears. The clock changes, the data appears. The data can appear at any point, and all the clock does is not powers the card, but allows the processor to run because underneath the card there's not enough areal to put a clock crystal. And this is what one of these bytes being sent looks like. If you're familiar with the RS-232 RS-232 serial port standard, then it's pretty much the same. The IO line stays at high, then it drops, and then exactly one time period, elementary time unit afterwards, then the next bit is there. There's 8 data bits, there's a parity bit, and then it goes high again, and the next one happens. So what the reader has to do is wait until it gets this, then it knows the time for inspecting all these other bytes. Like most ISO standards, ISO 7816 is filled with ridiculously large number of options, mainly because they couldn't make people decide on one of several completely adequate choices. So sometimes a high means binary 1, sometimes it means low. Sometimes you send the first bit first, sometimes you send the most significant bit first, sometimes the last bit. There are 6 different ways of encoding integers in this protocol for no good reason at all. So it's painful to work with, but that is what I'm essentially going to work with for the moment. So this is what we built, or mainly SAR built. On here, this board here is a Xilinx FPGA, and how it works is it monitors the IO line and it monitors it at 8 times the width of one of these bytes, one of the bits, until it finds this edge, and then it waits until the middle of the next bit captures that, the middle of the next bit captures that, and so on. It needs to be connected to the IO line, and also either needs to be connected to the clock line or it needs to be told the clock frequency, because the clock frequency can vary. It can vary anywhere between 1 megahertz and 5 megahertz. And the frequency of the data rate is that divided by 372. The reason it's divided by 372 is one of the cheapest types of clock crystal is the one that's used in American televisions. If you take this frequency and divide it by 372, you get 9,600 bits per second, which is compatible with standard serial ports. So that's another one of the strange things to do with the smart card protocol. In practice, these card readers work at very low frequencies, 1 to 1.5 megahertz, and the ones that you use in ATM or point of sale transactions run at the maximum, which is 5 megahertz. They run at the maximum because the few milliseconds that you save by running this at a higher data rate, when you add that up over all the transactions you do, actually allows you to fire some staff. So they are very concerned about the speed of these smart cards when they're doing transactions at the point of sale. If you're someone who's successful, then this makes a difference. The card then records all this data and then sends it off via USB to the PC. What we found is that the protocol used is extremely similar to EMV, that's the smart card payment. It's pretty much identical. It seems as if this card reader talks to the card and tries to initiate a transaction as if it's going to be used at a point of sale transaction, and it then cancels it at the last stage. But even when it cancels it, the card still generates a cryptographic message authentication code over the data that's been sent, and we thought that was what was going to be used, and we were right. The only difference is there are two data items that the card has which are not defined by the EMV spec. They're indexed by a tag, there's a whole list of tags in the EMV spec, and there's 9F55, 9F56 are on the card but not in the specification. So what we're trying to do is work out what these are and how useful are they for building a compatible reader. The other thing that we tried to do once we vaguely understood it was try to sort of change some data. And we already had the hardware necessary for doing this. And I talked about this at my 24C3 talk on the relay attack. I won't go into the details of the attack, but what we had is another FPGA board, and this is connected to a fake card, and all this does is provide a physical interface and electrical interface to a card reader, and this allows us to connect the card reader directly up to a PC and send arbitrary data to it. Running low on batteries. Okay, that's right. We then had an off-the-shelf smart card reader which we connected to the real credit card. So we could make the smart card reader talk to our credit card via the PC. We could read and change arbitrary data, and this allowed us to change something and then see what happened. Most of the things we changed made the transaction just completely fail, but sometimes we saw some differences. So sometimes if we flip one bit here, then that will cause a completely different code to be displayed on the calculator. Another time we flip one bit to a different place, and then only one bit gets flipped on the output. So what we discovered from doing all this was that there's a standard transaction, as if it's point of sale, cancelled at the last stage, and the card then outputs a whole bunch of data. The ones that are relevant are the CID, cryptogram identification data, and that's always 80, not very interesting. There's application transaction counter. This increments by 1 each time you do a transaction. There's application cryptogram, which is a triple days MAC, and then there's the issuer application data, which is something the card generates. Now, this amount of data is very long, it can't be displayed on the screen, and users will certainly not want to type it in. So there's got to be some process that this gets converted into 6 to 8 digit code. And by fiddling around with various things, for example, we sent the card reader all zeros and all Fs and half zeros and half Fs, we were able to work out the order of these fields and what that mysterious long bit of data was. That's sort of sometimes called a bitmask, sometimes called a bit filter. I'll explain what that does. So you take all this data, you then take the bitmask, which is normally zeros, and then you do a logical AND with it. And then you get some information that's mostly zeros. You then take all the ones here and keep those bits from here, and then throw everything else away. And then you get a very small bit of data, and that's the next decimal. You then convert it to decimal in the normal way, and that's what the calculator does, and that's how the data comes out on the screen. So to test this, we connected our credit card up to a normal smart card reader. We didn't use a calculator at all, and then we logged into online banking using it. So we've now tried this with several banks, and we're fairly confident that we've got a reader that's compatible with it, and there's a full specification of the protocol in the academic paper, which is linked to from the FAR plan. So what now happens is customer enters the PIN is sent to the card compares it with the one that's been stored, and if it's correct, it allows the transaction to continue. The customer then enters in transaction details, so we'll talk more about that later, and then the card takes these transaction details, encrypts it using triple DES, and then takes the last block. It takes a bunch of other data, like whether the PIN is verified correctly, the counter, the value of the counter, combines that with the bit filter, converts the result to decimal, and displays that on the screen. So there's no cryptographic secrets at all within these devices, so it's actually fairly easy to create a software compatible implementation of it. We've done one, and there's another one as well available. So now we've got the protocol, we were interested in what sort of failures were there. Was this perfect? Are there some holes in it? Are there some huge holes in it? One of the big problems is usability. These devices don't just have to be theoretically secure, they have to be usable, and customers should be able to use it in a secure manner. So for example, the TAN system was secure in a theoretical way, but what the fraudsters did was lie to the customer. They would tell the customer that you need a TAN to log in addition to using a TAN to do a transaction. Now, if you work for a bank, you know that that was never going to be the case. Most customers don't know about that and are not told about that, so they will enter in 2 TANs, and then the criminal's got 1 TAN you can use for fraudulent purposes. There are similar examples of this going on with the CAP protocol. Each bank uses the 3 different modes in a different way. These readers have got 3 buttons at the top. There's one which is identify, and that's where you press that, you type in your PIN, and you get a code after typing in nothing else. There's respond, where the calculator says number, and you type in an 8-digit number, and then it gives you a code. And there's sign, where it gives you ref and amount, and then you have to type in 2 different numbers, and it gives you output thing, and it's put an authentication code. These were intended to be used for fairly simple cases. You're supposed to use identify for login, respond for authorizing arbitrary transactions, and sign for doing account transfers. But each of the banks have gone for something slightly different. So Barclays did essentially that. You log in using identify, and then when you want to do a bank transfer, you type in the account number, you type in the amount, and then you get the authentication code. This means that the customer has to type in a 4-digit PIN, 6-digit account number, and say a 5-digit amount. That's quite inconvenient, and if they type anything wrong, it just will not work, because the authentication code will not match. NatWest instead went for a simpler method. They used the respond system, and what they're asked to type in is 8 digits. The first 4 are random, and the last 4 are the last 4 digits of the account number you want to transfer to. So this has all the good properties, because the transaction authentication code is bound to the destination account number, but it's really not obvious to the customer that this is the case. You're asked to type in 8 digits, they'll actually type this in, and the customers will type them in. They wouldn't compare the last 4 digits of that number against the last 4 digits on the account number that they want to transfer to. So that's precisely what fraudsters have been doing. They bring up a fake online banking login screen, and they say, you need one of these codes to log in. Exactly the same as what people were doing for German banks against the TAN system several years ago. You then give one code to log in, that goes off to the fraudsters, they do something evil with it, and then you're in, and then you can carry on the transaction. Everything seems to work fine for you, except some money disappears from your account. So because of this usability failure, you've turned a theoretically secure system into a practically insecure system. Another problem is a cryptographic issue, which is that the button you press doesn't actually control what your card is going to calculate an authentication code over. So I mentioned that when you type details into this device, it's effectively doing a transaction with your card. When you're doing an identify transaction, it tells your card that you're doing a transaction for £0, 0 pence, and it also asks for a random number, and it's being sent a random number of zeros. This and a bunch of other detail goes to the input of the triple DES authentication code calculation. When you press the middle button, the respond button, it's still for £0, 0 pence, except the random numbers are replaced with the challenge you type in. And when you do sign, the amount you type in goes into the amount field as you expect, and the random number, what the card thinks of the random number, is actually the account number. But what you'll notice here is that if you do one of these sign transactions, and type in £0, 0 pence, you get exactly the same as a response transaction. So this gives the crooks another way of committing fraud. What they can do is say, we know you are not supposed to use a response transaction because that's how you do an account transfer, but we need to resynchronize your account, or there's some problem, or tell some other plausible story. And to do this, we need you to do a £0, 0 pence transfer to this account number. And you think this is fine because it's £0, 0 pence, but what you're actually doing is authorising an account number, authorising an account transfer to somewhere else. Now, when we posted the description of the protocol on our blog, Light Blue Touch Paper, a commenter came from one of the banking service providers and said that actually you made a mistake here. The calculation includes is not just this, but also a flag that says which button you pressed. So we got a bit worried about that, and then checked over all the hex dumps and tried some experiments, and turned out we actually were correct and the commenter was wrong. So we told him that, and he then said that the original version of the specification didn't have this bug, but the bug was introduced later on for very similar reasons that was talked about in the deck talk. The engineers found some problems with the way that the card protocol was going to be done, so they made the simplification, which sounds okay, but actually might not be. Another issue is that although there is a nonce, a number used once in these transactions for the NatWest variant of the protocol, which is a random number, it's very small, it's only 4 digits. So this means that you can take someone's card, because you're pretending to be a shop, ask for 100 challenges from it, just by guessing random nonces, and then you log on to the online bank and ask for trying to do 100 transactions. And there's a 63% chance that there'll be a match from one of these bits of data you've collected and when you log onto the bank. This is because of something called the birthday paradox. There's a 1 in 365 chance that you have the same birthday as someone else. But when you have a room full of, I think, 23 people, there's a 50% chance that there are 2 people the 2 people have the same birthday. So because of this counterintuitive result, even though there are 10,000 different possibilities for the random number, you only need 100 guesses to get a 50% chance at guessing this correctly. But Barclays don't use any nonce at all. They just ask for your account number and the amount you're going to transfer when you want to do a transaction. So crooks can exploit this in a way which I've demonstrated in a television program, and I'll show you a snippet of what's going on. It's about 4 minutes long.
Peterborough has a busy high street. On the way down here, I counted 5 cash points. We don't think twice fuss about using them anymore. They're everywhere, and we use them all the time. So imagine if you found out that someone was stealing from your bank account, but instead of getting your money back, you were arrested and accused of fraud. Well, it happens, and according to the expert you're about to meet, it could happen to any of us. Millions of us shop and bank online, and just about all of us will use a cash machine at some point this week. Convenient, yes, but how safe is your hard-earned cash? Millions of pounds are taken by fraudsters every year, and you may be surprised to learn it could be you who pays when things go wrong. To find out how and why, I've come to Cambridge to meet a team of computer hackers. Breaking into security systems is what they do. Fortunately, they're not fraudsters.
Over the past 15 years or so, banks have repeatedly claimed that their systems, card payment systems, online banking systems, were secure. Again and again and again, we get people complaining, coming to us saying, "Oh, I was the victim of fraud. The bank says that I didn't take care, but I did." And again, we've investigated these systems, and we found all sorts of loopholes, all sorts of design errors, all sorts of implementation blunders that allow fraudsters to exploit people's accounts and steal their money.
In the past, the team has proved weaknesses in cash machines and PIN terminals. Now they've turned their attention to the latest online anti-fraud system. Banks are constantly trying to stay one step ahead, so some of them are giving their customers handheld card readers to use online. And what they do is they give you a unique code every time you use them. But now Sar and Steve are going to show me how they can break into even this system. All they need to do is get the customer's name, the unique PIN code, and their account membership number. Now, this customer knows what is happening, but if this was a real fraud, she would have no idea the chip and PIN terminal she's about to use has been rigged. While she's using it, her data is being collected on a laptop linked to the terminal.
From that fake chip and PIN terminal, we've collected the victim's name, and we've also got one of these one-time codes which can be used for online banking. Now all we need is their membership number.
The membership number isn't something you have to protect particularly.
No, it's not something that you're expected to protect. So I think it would be extremely plausible for a fraudster to call the customer and say, "This is your bank, we've seen you play this transaction in this shop, did you really do it? That's fine. Can we get your membership number just to confirm who you are?" And I think most customers will hand it out. And with those details, we can now log into the online banking and do as many transactions as we want.
Okay. So you've got the surname. Mm-hmm. Steve now has the one-time code from the chip and PIN terminal and the customer's bank membership number, and it works. I watch him log in and even transfer money out of her account.
And that's as into the online banking system.
That's right. So that's simple. You can get into her account or anybody's account through that process.
Yes, and a fraudster could do this very easily by hand. They could even automate it.
Is this something that fraudsters are already jumping on and using as the next thing to trick people out of their money?
I think fraudsters are probably already attacking systems using card readers.
Okay. So what was going on there is the victim plugs in their card, which they use for point-of-sale transactions, into this fake reader. This is the same one I made play Tetris a few years ago. And rather than doing a point-of-sale transaction, it asks for their PIN and then pretends to be one of those handheld card readers and gets the authenticating code, sends it off wirelessly to a crook who then can just manually type it into the web browser and log into the online banking, or you could automate it and have the PC automatically go into the bank website and do that fraudulent transaction. Another problem is that criminals can use these card readers to check whether a customer's PIN is correct. What they used to do was they would mob you on the street, ask for your card, they'd then have to march you past all the CCTV cameras to an ATM and then ask you to type in your PIN so that they get the correct one. Now they can do this when they want because they've got one of these and this will tell whether the PIN is correct. And another one is that we've made a software implementation of CAP. Another group working for Andrews and Arnold's ISP have made one that works with only Barclays, but this will allow you to plug your card into your PC and then use it for doing automated online banking. Now this is very convenient, but it's also fairly convenient for the fraudsters, because if they can, lots of people use this software and they break into your PC, they've now got your PIN, because you have to store that, and they've got your card details and can use this for doing fraudulent point-of-sale transactions and potentially also the ATM transactions as well. Another thing that criminals could do is infiltrate the supply chain. These things appear in the mail unannounced sometimes, so maybe you'll get one for your bank one day and maybe you'll get another one that comes from the Russian mafia, and what that does is read your card and then send your details off over a GSM module that's embedded in this, and then they can use it for fraudulent transactions. Now that won't be very cheap. GSM modules are expensive, but if you are going to do large value frauds, so-called whale phishing, then that starts to become an option. These things are now going to be used for chaps transactions where you can transfer hundreds of thousands of euros, and if you're going to steal that, then you can afford to invest in a GSM module. And criminals are already doing this for point-of-sale transactions. These chip and PIN terminals are made in China. Sometimes you'll get one that's correct, and another time you'll get one and it's actually been backdoored in the factory, and then it sends your details off to Pakistan, and then you're defrauded in Malaysia. In the UK, someone had to go around and weigh all the chip and PIN terminals to see if they had some extra electronics added, and a lot of them did. But what does this actually mean for customers? Now, although CAP has some problems, it's certainly better than all the predecessor systems used in the UK. It's using a dynamic password, so you can't just use a simple keyboard logger, and it's imperfectly bounced on transaction, but at least they're trying. So is this better for the customers? It might not actually be, because the consumer protection laws in the UK are vague and fairly weak. They say you're protected, but only if you haven't been negligent. And what happened to customers when they moved from authorising point-of-sale transactions with signature over to doing it with PIN is that if a fraudulent transaction happened to you, then they would say that you must have disclosed your PIN, therefore you're negligent, therefore you're not getting your money back. And now 20% of the victims of fraud in the UK don't actually get their money back. So now that UK is moving to authorising online banking transactions by PIN, will that make the same thing happen there? Now these are new, it's a bit too hard to tell, we don't have the figures, but it's certainly a possibility. And the problems that we come up with is the banks usually use fairly vague ways to justify why they believe you're being negligent. This is a letter that was sent from the Financial Ombudsman to a card fraud victim, and I'll read it out for those who are at the back and you can't see. This is where the Ombudsman says that the firm, the bank, has provided the audit trail of transactions disputed by you. This shows the location and times of transactions, and the evidences that the card used was chip read, i.e. this was a shipment transaction. Although you question the firm's security systems, I consider that the audit trail provided is in the format utilised by several major banks and therefore can be relied upon. Although you have requested this information from the firm yourself, the customer wanted to pass that details on to an expert, and I consider that it is not obliged to provide it to you. I conclude that this will not make any difference because this service has already reviewed this information. As we've already advised you, since the advent of chip and PIN, this service is not aware of any instance where a card with a chip has been successfully cloned by fraudsters so that it can be used by them successfully in a cash machine. My conclusion, therefore, that it's likely that the original card was used to carry out the transactions disputed by you. Now, this went to court, and the customer actually lost, and the bank did have some information on the transaction logs that would include whether it was chip read or not, but they had deleted that by the time of the trial and you didn't know why. But they did list a copy of the log file that I mentioned, which is in the standard format, and I'll see if I can get that. just use it. Here we are. Okay, here's the log file format, and I can zoom in. And the evidence that shows that chip read is this 04, because apparently with chip transactions, 04 transaction 04 means a chip read, and anything else means it's not. And that was really the sum of evidence that was presented in that case. And the discussion over what log file format it was is it's in the EBSTIC. EBSTIC is one of the predecessors to ASCII, developed by IBM, and it really shows you no information on why that log can be relied upon. But that customer lost, and he had to, well, he was made liable for the bank legal fees, because that's the way it works in the UK, and I think that was £15,000 or a £4,000 transaction. So even if he thought he was almost certainly going to win, and he wasn't really sure, then a rational person would never sue a bank, because you're disputing a small amount of money, and if you lose, you're going to lose your house. So other countries have done some things better. So in Germany there's something called HHD 1.3, which is very similar to CAP. The card readers look the same, the protocol is slightly different, and they fix some of the problems. So rather than just being these three modes, which you have to press buttons to get on, there's a number that you type in given by the bank, and then this controls the type of transaction you're going to do, whether it's going to be inland transfer, domestic transfer, or change your mobile phone number, or doing all sorts of things. There's always a nonce, so you can't do one of the frauds that we did in that video, where you collect the details at one point and then use it later on. And the mode number is also included in the MAC, so you can't fool the customer to give you an authentication code for one mode by getting to type in something in another mode. And also PIN verification is optional. So if you've got a card which doesn't require PIN verification, then criminals can't mug you and then use one of these card readers to see whether it's okay. There are some other systems that use similar technology. There is RSA Secure ID and Recal Watchword. Rather than doing PIN verification on the card, they do it on the server, and that means that you can have duress pins. So you can say that I'm being mugged, let this transaction go through, but then don't let it be used for anything else. And there's other improvements that can be made, and these require some modifications to the bandwidth that's being sent. The reason these systems are sometimes insecure is that you have to type in lots of numbers in here, and that's inconvenient. And if you type in anything wrong, it won't work. So the banks have optimized it to the extent that it's no longer secure. But if you can improve the bandwidth just in one direction from the bank to the device, then you get you have opportunity for a more secure system. So this one is called FlickerTan. I don't know if anyone's used it. Sparkas are offering this. And here, when you log onto your online banking, you hold the reader up to the screen, and this is an animated GIF which flickers on and off, and then some photo sensors in the card reader which then contains the transaction details. They're displayed on the screen for you to confirm, and then the rest of the transaction happens as with the HHD 1.3, and you type in the authentication code it gives. You can also plug these things into the PC, and then you've got as much bandwidth as you need. This is a class 3 card reader, so it's got a display and a PIN, so you can confirm the transaction and type in your PIN if it's okay. A major problem with this is that it needs drivers for major operating systems, so you can't do your online banking at work. You might not be able to plug anything in, and a lot of people do online banking at work. So another one, which is what I've been working on, is using your mobile phone to do online banking. This isn't based on HHD 1.3, it's more versatile. You can encode arbitrary text into a 2D barcode, which you are shown at the confirmation stage of online banking, and it gives you an authentication code for you to authorize the transaction. and I can give you a demo of this, hopefully. So let's turn on the video camera. Okay, this is me. And not go to there, let's go to here. So here's a demonstration of an online banking application. I'll log in, and then I'll do a transaction, say, dragons. 1, 2, 3, 6, and then it shows me this barcode on screen, and I'll take this over here and start up an application on my phone. So this is what the application looks like. It's got a camera on it. And then take a photo of this with the camera. And then that's what it shows on the mobile phone screen. So it's asking you to confirm whether this is correct. It shows who you're paying to, the account number and limit, and if that's all okay, then you type that in and the transaction will go ahead as normal. If anyone wants a demonstration close up, then no. Yes, question?
The man in the middle can fake the barcode.
They can't fake the barcode because this thing has a cryptographic key. So the customer knows that the bank really sent that barcode. So the fraudster can generate a fake barcode because then the phone will just say this can't be decoded, the authentication code will fail. And if the crook sends the wrong details to the bank, say they want you to pay some money off to Latvia, then the barcode will be valid because it's generated by the bank, but the details that are shown in your phone won't match the things you typed in, so you should spot that. So that's why it says at the top, and confirm whether this is correct, and if the details correct, type in that code. Okay, so in conclusion, I've talked about the necessity of transaction authentication, and we reverse engineered the UK CAP implementation and showed how it wasn't bad, but it wasn't great either. There's usability and security flaws, and by combining point-of-sale transactions with online banking transactions, it gives the criminals some ways of exploiting the system. Usability testing is an important part of trying to build secure systems because that's exactly what the fraudsters are going to exploit, and more bandwidth is necessary in order to improve the usability and security. So the system that I've been working on is now being used by Commerzbank, and the customers generally seem to like it there. Okay, so anyone have questions?
Just a second, that was really cool. I don't trust this thing. Okay, if you have a question, please come up to the mic. The mic stands right there. And there's one back there too. And Stephen, could you please repeat the question for the camera? Thank you.
How are the keys provisioned onto the phone? The phone has its own keys and an individual key linked to your account.
Yes. So this is up to the bank, which is... Sorry, I'll repeat the question. The question is, how are the keys loaded on to the phone? This is up to the bank itself, but how we've done it in the trial so far is they are sent a letter which has a printed version of a barcode which contains the key. This is convenient because banks already have a procedure for securely sending mail to your address, but it could equally be provisioned online or over the air. That's up to the provider itself.
You didn't mention the German mobile TAM procedure using a GSM phone. Do you think that is secure?
Yeah, so for background, the MTAN system is where you are sent as an SMS a description of your transaction and an authentication code. This isn't bad, but there are a few problems with it. One of which is it costs quite a lot of money to send an SMS for every single transaction, so the banks don't like that very much. The other problem is that you're relying on the mobile phone network to secure your transaction. And in South Africa, there was a case where gang of criminals impersonated a person in order to get a duplicate SIM card for their phone, and then used this for carrying off €100,000 worth of transactions. The bank then went to the phone company and said, "You screwed up. You gave a copy of the SIM to the wrong person." And the mobile phone company said that we're a mobile phone company, not a banking security company. It's your problem. So what the bank in that case did is just refuse to refund the customer. So by bringing the mobile phone company into your trust, the people you have to trust, you might be introducing a problem. Whereas although the Pronto system works on a mobile phone, it's not really being used as a mobile phone. All it is a CPU and a camera that runs an application. So you don't have to trust all the other applications on the device. And if you're worried about that, then the banks could send them a dedicated device that just has a camera and a screen and nothing else, doesn't run any code. So it's a safer option, even if the mobile phone company is acting maliciously.
Just one note to that. Another problem with the MTAM system is that often you have in your normal online banking the option to change your phone number using one item. So with an attacker, if you someone get an item from the user by phishing, then you can change it to your own phone number and request arbitrary number of further items. So that's again a usability issue there.
Yeah, so for all security systems, they're only as secure as the weakest link. And if there was some way to change the identity of a customer, then yes, you could bypass any type of security system. So one thing that troops in the UK will do is ask for you to be sent a new PIN, and then they will stick to the outside of your door a second letterbox. Your new PIN will be delivered to that letterbox. They then come along, take the letterbox away, and then you think everything's going fine, but the criminals have got a copy of your PIN.
I have a question regarding the terminals at the shops and so on. You had in the video the example with a laptop connected, but usually it's a little bit hard because in German you have often people at the cashiers, and in America even at the there are also people watching over. But I have seen one time I was shopping in a store and they had such a thing with a GSM module in it. And I was wondering how secure are they, because I can stand outside and get the data from them or try to get it. I don't know how secure they are. I was wondering if someone has already looked into this procedure.
I'm not sure. I haven't looked into the security of these wireless terminals. They're supposed to have encryption, but the interesting question is, have they added their own encryption? Is it good, or are they just relying on an encryption that already exists? So these things are GSM and Bluetooth. Both of these has encryption, but we know very well that these encryption algorithms are not very good. So yeah, I'm sure there's potential for vulnerabilities here. I haven't looked myself.
There's at least one British bank that uses the same system that you've outlined, only without the card reader. That is to say, there's a gadget everyone's got is specific to that person. You then only have to give in the PIN number personal to you, and therefore that gadget, without introducing a card reader into the system. Does that have any substantial either advantages or disadvantages?
So I know several UK banks issue an RSA Secure ID, which it looks like one of these, except it doesn't have a card reader or a keypad, just got a screen. That's not very good because the number that is generated by this only depends on a key and the current time of day. It doesn't depend on the transaction. So a man-in-the-middle attack can trivially defeat that.
The one I'm thinking of does introduce, you also have to give in the details of the account number and the amount that you're paying.
Okay, so I don't know that one. I guess that's related to Recal Watchword. That does sound better in some respects because you don't have this card. It's a lot more expensive for the banks because tracking which user has got which device actually significantly increases costs, and I can imagine why that's not more widely deployed.
It's a bank with a very small number of customers.
Okay, they can probably afford it.
Okay, unfortunately, we only have time for 2 more questions. After that, we'll have to take it to a breakout room. Here you go.
Just a quick question from my side. Since although the system is flawed and the bank refuses to pay and the customer has to stock up everything, is there any change or anybody pressing in the UK for a change of the legal situation so that at least the customer is not stuck with the bills?
So there has been a change as of the 1st of November this year, which is a very late implementation of the EU Payment Services Directive. The Payment Services regulations in the UK implement that and say that the customer is not liable for fraud. The problem is that the regulator responsible for this, the Financial Services Authority, have decided that rather than implementing those rules, they will just do what they consider, in their opinion, to be fair. And they're allowed to do this because of the way it's set up in the UK. The only way you can actually use these new laws, which do give good protection, is to sue the banks. Then you have the problem that they will throw their best lawyers at you, and if you lose your house. So far, I only know of 3 cases against the banks. 2 of those were criminal, and the customer won in those cases because in criminal cases you don't pay the other person's fees. But in the one civil case, the customer lost.
Okay, one more.
Okay, so you've touched on the fact that the banks are very sensitive to the per device cost in terms of the unique ID keys for each user problem. You also touched on the fact that when you have the mobile system involved as part of the security system, that the phone company isn't willing to accept liability for that, and it's the customer who winds up with the cost. So the system you have implemented now is on a mobile phone.
Yeah.
If the phone is compromised, the manufacturer of the phone, the people who write the software for the phone can say, well, this was a phone, not a security device. Potentially the payout then falls back to the customer. Do you think the banks will pay out the extra cost, given you've already said that's an issue, to do an actual customised device?
So the banks are very sensitive about cost, but they will buy things if it's necessary. So the mobile phone right now is very convenient because the customers have already got it, so there's no extra cost. It's convenient to the customer because they're already carrying it around. And right now mobile phone security is actually pretty good, certainly compared to PCs. But it's true, if you compromise the phone and the PC, or the phone and the network, then yes, you can commit fraud. So at that point, when there is actually significant fraud, and hopefully the customers will be refunded for this, then the banks will be able to invest in the money necessary to roll out these devices. But they will be cheaper than the devices that have preloaded keys, because just like these calculators, they don't have to have preloaded keys. You can be sent the same device as everyone else, and then just with the phone, as with the phone, you're posted a barcode in the mail. You take a photo of that, and that device is then yours.
Yeah. So it still needs a camera and a CPU and a screen, which is a lot more than
Yes, so it might be more than these devices, but because of demand for small cameras for phones, the cameras that we put in these things, they don't have to be very good, are actually rather cheap. We'd have to wait and see how much it will cost on the market.
Are you willing to take other questions and stuff in the bar?
Yeah.
Please, one drink.
Sure.
Awesome. Okay, please meet Stephen in the bar for any additional questions. This is an awesome talk. Thank you very much.